Thank you, Mrs. Chairman. Today, I would like to talk about the recovery of valuable metals from EAF slag by microwave-assisted leaching. This work was carried out at BRGM, the National Geological Survey, as part of the French High Pass project funded by the French National Research Agency. Currently, we notice the depletion of natural resources in the world, and there is a strong demand for primary resources of metals used in high technology, while these metals become depleted in the future. One of the solutions to solve this problem is to get these metals from a secondary resource, such as metallurgical byproduct containing metals like chromium, vanadium, or molybdenum. To recover these metals, there is a need for more efficient technologies in order to minimize the expenses, the environmental impact, and to meet the increasing demand of these metals for the high-tech. Slags could be a very good secondary resource, as they contain high content of different metals, chromium, and strategic metals. Therefore, they should be viewed as a resource, not as a waste. The challenge is to be able to selectively recover valuable metals like molybdenum, chromium, or vanadium, and this by knowing their physical-chemical properties. A representative sample of slag recovered from the electric arc furnace supplied by the French steel industry was characterized and processed in order to recover chromium, vanadium, or molybdenum. The objectives are to develop a methodology to recover strategic metals contained in EAF slag by using innovative alkaline leaching, conventional and microwave roasting followed by leaching. To classify its efficiency compared to the conventional roasting process, and to valorize the residues obtained from treated slag. The investigated slags were provided by the French steel industry. The slags were landfilled for several years because there was no technology available to valorize them. According to the new legislation, these slags must be treated and valorized. For now, the French steel industry has removed the iron scrap by primary magnetic separation and sold the treated slag for further processing. This flowsheet represents the methodology applied in this work. After sampling and grinding, the iron scraps were removed by dry low-intensity magnetic separation. The slag free of iron scraps were again crushed and grinded to obtain a size fraction of 125 micrometers. Different alkaline reagents, such as sodium and potassium hydroxide, sodium and potassium carbonate, were tested for leaching the metals contained. Co-grinding of the slag with reagents for 1 hour was applied in order to obtain a homogeneous mixture. The mixture was then roasted in microwave under different parameters: power, residence time, and humidity. The dynamic leaching in water was carried out on the roasted sample. After filtration, the solution and the residues obtained were characterized by conventional analytical techniques. LDH, layer double hydroxides, were tested to recover the dissolved metals. After filtration, the solution was analyzed to calculate the recovery rate of each metal. A representative sample of steel slag was characterized, and the following table shows the chemical composition of the investigated steel slag. It shows that this slag contains 3.4% chromium, 154 ppm molybdenum, 1450 ppm vanadium, 48% iron oxides, and 5.2% manganese oxide. As shown by photos taken from scanning electron microscopy, this slag is very heterogeneous. The X-ray diffraction reveals the following crystalline phases: lernite, magamite, cerebrodolskite, hematite, wostite, chromite, magnetite, and quartz. The Mossbauer spectroscopy gives different valences of iron, and it shows that the slag consists of more than 50% of paramagnetic compounds. The preliminary tests were carried out on the microwave roasting of different mixtures of slag with different reagents for 10 minutes. The figure shows the best results obtained. It shows the leaching rates of these mixtures as a function of the roasting temperature. It is found that sodium and potassium carbonates do not react with slag. The temperature of the microwave is low, and that potassium hydroxide and carbonate have good reactivity with the slag by increasing the temperature, and the leaching rates are the highest. The microwave roasting tests were performed on wet and dry mixtures, slag with reagents. The figure shows the results obtained, and it shows the leaching rates of chromium, vanadium, and molybdenum for different mixtures roasted in dry and wet processes. It can be seen that the highest leaching rate of chromium is obtained for the mixture slag with potassium hydroxide plus sodium potassium carbonate. This slide summarizes different results obtained from microwave roasting assisted leaching of chromium, vanadium, and molybdenum in different microwave roasting conditions. The figures show the evolution of leaching rates of the desired metals as a function of microwave residence time for 1, 1.2, and 1.4 kilowatt. It is noted that the leaching rates of chromium and molybdenum are close to 100% for 15 minutes of roasting of the slag with potassium hydroxide. The same results are obtained for 1.2 and 1.4 kilowatt. The leaching rates of vanadium are low for all conditions. We can see that the leaching rates of these metals are low for the mixture slag with potassium carbonates, and it seems that this reagent inhibits the reactivity of potassium hydroxide with slag. See the results shown in the right figures. This table summarizes the results obtained from conventional and microwave roasting assisted leaching. It can be seen that the best results were obtained when the mixture of slag with alkaline reagents were roasted in the microwave during 15 minutes. However, it takes 1 to 3 hours roasting in conventional furnaces, and the leaching rates are below 98%. The investigated slag was generated from EAF process provided by the French steel industry. The characterization was performed by different conventional techniques. The results of the chemical analysis that the investigated sample of slag contains 3.5% chromium, 48.5% of iron oxides, 1,450 ppm vanadium, and 154 ppm molybdenum. XRD analysis reveals the following main crystalline phases: Laranite, cerebrodolskite, hematite, magnetite, magemite, and wustite. Compounds carrying chromium, ferrites have also been detected, although these elements is also dispersed in various other mineral phases. Mossbauer's spectroscopy shows different iron valences, and it shows that the slag contained more than 50% of paramagnetic compounds. This modification process allows the leaching of a high proportion, in particular of chromium and molybdenum. Conventional roasting, 2 hours, leaching rates 97.50% chromium, 62.50% vanadium, 95.80% molybdenum. Microwave roasting, 15 minutes, leaching rates 100% chromium, 65% vanadium, and 100% molybdenum. The obtained results seem promising in terms of efficiency. It remains to validate the profitability of the complete process in the ongoing project. The authors warmly thank the financial support of the French National Research Agency, which made this collaboration possible with other partners of the research project, as Armines, Spin, and Industeel. Thank you for your attention and waiting for your questions.